How to design strong parts. So the simple answer is just to have as much material as possible, but in the real world we have restrictions such as size, weight and cost, which means that we kind of have to go about making strong parts in a bit of a smarter way. So assuming we have some sort of limitation on how much material we can use, where do we actually want to put the material? Well, that question somewhat depends on the type of loading that the part's going to experience. So with tensile and compressive loads, luckily the answer is very simple. We just want to maximize the cross-sectional area in the direction of the force that's being applied. So two bars of the same diameter, one of them hollow and one of them solid. The solid bar will experience less deformation because it's got a greater cross-section area. But with bending loads, it's not actually as simple. So if I take a bar like this and I try and bend it, the material at the top of the bar is going to experience a tensile load if I'm bending it like that, and the material at the bottom of the bar is going to experience a compressive load. And the material right in the center of the bar, so if you imagine a line going right through the center of the bar all the way through, and I'm bending it, that material is actually doing nothing. It's not contributing to the bending resistance whatsoever. And so because of this, if we take these two tubes have exactly the same cross-sectional area. So if we take the area at the front of that, area at the front of that, it's exactly the same. So it means they weigh exactly the same, they're exactly the same amount of material in either of these tubes. However, this one is hollow and this one is solid. And so because this one's hollow, there's more material spread out away from the central axis. And so that means if I try and bend it, it's really, really hard to bend. Whereas this one, even though there's the exact same amount of material, because it's more central, that material is having to work a lot harder, and I can feel it. It's a bit more bendy. So for any beam, the bending resistance isn't just related to the cross-section area, but also the distance that material is spread away from the central axis. So this is why if you're into 3D printing, if you want to increase the strength of your 3D prints, you're typically told to increase the number of walls as opposed to the infill. And the reason for that is simple. It's because the walls actually contribute more to the bending resistance of that part than the infill actually ever will. So it's worth mentioning also that the increase in geometric stiffness by moving material away from the center, it's not a linear relationship. So even with this hollow beam here, this hollow bar, if I were to move even a tiny bit of material further away, so if I were to make it slightly wider, the increase in geometric stiffness is much more than the amount that I've moved away from the center there. So this concept is known as the second moment of area. And if you want to find out more, I'm going to leave some links in the description so you can learn more about that. There's a ton of equations that you can use that, for example, that I use to work out these having the exact same cross-sectional area, but this one is, I think, 4.6 times stiffer than this one. So next we're going to talk about adding stiffening structures to your parts. So for example, this corner bracket here, if I were to imagine bending it, I don't want to break it yet, but if I were to imagine bending it, all that load is going through this tiny little bit of wall here, right at the corner. So if I'm trying to pull it apart or push it together, all that load is pretty much going in that tiny bit there. And so like before, we want to move material away from that small tiny axis there. And one way we can do that is with ribs. So here we've got the same bracket, but with some ribs on either side. And this is just moving material away from that corner there. And so if we try and bend this, it can feel it's much, much stiffer. And this isn't as far as we can go. I mean, for this part, you can imagine it being a sheet metal part where you've got the sheet metal bracket and then two parts sort of welded onto the side as the ribs. But you can also do something like this. So this is actually even more efficient with just one part going between these two, forming a triangle there. And why is it better? Well, it's because we've moved material even further away from that central axis, and it's all along this as sort of a flat plane. And so this one is, I mean, it's not a massive difference, but it is noticeably more stiff than the previous one. And you'll see on screen that I did some finite element analysis just to see how much difference there is in between these brackets. And as you can see, as predicted, the one with the sort of triangular brace perform better than just the ribs on their own. So it isn't just geometry that plays a part. The material we decide to use plays a massive part in how we design. So it's pretty well established that steel is much stronger than aluminium, but it's also much heavier than aluminium. But how does this actually affect the design of our parts? So let's take a steel tube of 20 millimeters outer diameter and 1 millimeter wall thickness. This tube will weigh 468 grams per meter, and if it's made of mild steel, it will cost 75 pence. So if we want to make an aluminium tube of the same mass and the same bending stiffness, we end up with an aluminium tube of 21.42 millimeters in diameter and a 3 millimeter thickness. and this tube will cost nearly 4 times as much as the mild steel tube. If instead we made that mild steel tube from 3 or 4 stainless steel, it would cost about 3 times as much. So cheaper than aluminium, more expensive than mild steel. So you might be saying, well, it's obvious we just make that tube out of steel then. Well, because that tube has such a thin wall section if it's made of steel, that tube will be liable to buckle, especially if it's loaded in compressive loads, or even in sort of localized bending loads where the tube just kind of squashes because the wall section is so thin. So even though the aluminium tube is wider, has a thicker wall, and is also costs a lot more, it might be the right choice depending on what you're doing, especially if you're loading the tube in compressive loads or kind of joint compressive and bending loads. So what if we wanted to keep the cost the same between the aluminium tube and the steel tubes while also keeping bending stiffness the same? So compared to the mild steel tube, we end up with an aluminium tube that is 36 millimeters wide and has a tiny wall thickness of 0.41. So this is obviously no longer viable. The wall thickness is just too thin and it will just buckle no matter what you do with it. But compared to the stainless steel, we get a bit of a better compromise. The aluminium tube ends up being 23.38 millimeters and has a wall thickness of nearly 2 millimeters. So that's a more usable tube. We can actually use that without expecting massive buckling. So it just goes to show that depending on what your limiting factor is, whether it's the size of the tube, the cost, or whatever it is, that determines what material you'll use and also what you're willing to sacrifice in the part. So finally, we're just going to look at a few existing products and to see how they use good part design to create strong, efficient parts. So first we're going to look at cars. So cars, they've got a bunch of thin sheet metal body panels that go all around them, but they're never truly flat. And the reason for this is because if they were flat, you'd have material right in the center, but you wouldn't have material spread either side. So these would be really easy to dent and they'd be really flexible. So really, car panels will have creases all over which help with the rigidity and the stiffness of the parts. And if you look at things like car hoods or bonnets, they'll be made from sort of 2 sections. You have the outside shell, which is what you see on the outside, and it is pretty much flat. And then on the inside, you'll have other structures that kind of help create that separation between the 2 halves and creates massive stiffness increases, as opposed to if you just had the outer shell. And all of this remains really lightweight because the stiffening structures inside remain pretty skeletonized and minimal. So to show what I mean about the car body panels, I've got this piece of tape here. What has this got to do with a car body panel? Well, it's flat and it's got basically a very thin wall thickness. And so if I try and bend it, it's very easy to bend it. It's very flexible. But if I take this piece of tape where we've kind of got a crease in the middle and I try and bend it along that crease, it becomes much stiffer. I mean, obviously I can bend it if I want to, but it's much stiffer in that direction so long as the crease doesn't kind of fold over itself and sort of flatten to the side like that. But if the crease is up and I try and bend it, it's very difficult. And that's because the material is separated away from the kind of main flat of the piece of tape. And so that's why car body panels and other flat panels, they're rarely completely flat. They'll always have some sort of creases and design features that you might think are there just to look nice and just to create some visual interest. And they do that, but they also are there to stop the sort of flat panels just flexing and all over the place. Another interesting one is conrods in cars. So the conrods, there's kind of 2 types of conrods. There's your I-beam conrods and your H-beam conrods. And it's kind of an interesting discussion because in an I-beam conrod, where the shorter sides have the most material, that kind of makes sense because the conrod is loaded in that direction and it's trying to snap the conrod in that direction under normal loads. But on the other hand, that's also the longest side, so that's also going to get the most material anyway. So does it need to be reinforced in that direction? Well, then you've got the H-beam conrod, where the flat sides have the most amount of material. And the thinking behind this is because the flat sides are separated not by very much material, they probably need to have a completely flat surface in order to resist bending. But the conrod isn't really bent in that direction. It's bent in the direction that the I-beam is strong. So because of this, there isn't really that much difference in reality between I-beam and H-beam conrods because the advantages of moving the stiffening structures to one side is kind of countered by other factors. That's all I've got for you for now. If this video has been helpful, then let me know in the comments. Feel free to subscribe for more of this. Anyway, I'll see you later.